Transfer function of a separately excited DC motor. So the DC motor can be modeled like this. So which is this is called armature part, and this is field part. The field is excited separately. The motor is loaded with a load having the moment of inertia J and the frictional coefficient P, and a load opposite torque is TL. The motor is running with the speed of capital N. Now the analysis part can be combined into two ways. First one is electrical analysis, and the second one is mechanical analysis. Now this circuit is the electrical analysis, where we have the supply voltage is armature voltage EA, armature inductance, armature resistance, and EB back EMF EB. So that can be drawn like this electrical analysis. So from this circuit we can write the apply Kirchhoff's current law. That is KL is equal to Kirchhoff's Kirchhoff's voltage law. Applied voltage EB is equal to drop in resistor IARA, and the drop in the inductance L into DI drop in the inductance plus back EMF. So this is equation 1. Again we know back EMF is directly proportional to speed, rate of change of angular displacement speed. So this speed we can write d theta by dt, that we can write n. So to remove the proportional, I am adding the constant Ka pi. So this Ka pi is called motor constant. This is called motor constant. Now the second analysis is mechanical analysis, where we have the load having the T is the applied torque. There are three opposite torques generated as we told here. The load having the moment of inertia J, that will generate one opposite torque Tj, having the frictional coefficient that will generate opposite torque Tb, and this load itself generate one torque, that is TL. So therefore this applied torque is supposed by three opposite torques, that is a TL, Tb, and Tj. So TL is as it is, we will try. So this frictional torque, that we can write P into d theta by dt, and this moment of inertial torque J into d square theta by dt square. So again this equation can be right. So instead of we are substituting from the d theta by dt, we can write n by replacing d theta by dt is equal to n. So the previous equation becomes like this. So this is equation 3. Again in DC motor, torque is directly proportional to armature current. To remove the proportional, we are adding the constant Ka pi. So this is equation 4. So therefore we have written 4 equations. The first 2 equations is related to electrical analysis. This equation is related to electrical analysis, and equation 3 and 4 is related to mechanical analysis. Now we will take Laplace transform of all the previous 4 equations. When we take the Laplace analysis of the first equation, EA is equal to IARA L into di by dt plus EB. When we take Laplace transform, so this becomes IARA plus this is the Laplace transform of equation 1. Then you take the Laplace transform of equation 2, that is EB is equal to Ka pi into n. So this EB becomes EA of S. So EB of S is equal to Ka pi into n of S. Again in equation 3, this T is equal to TL plus this equation. When we take Laplace transform, this will become like this. And the equation 4, when we take a Laplace transform, T is equal to T of S. This is constant as it is. When we take IA of S, I of IA, that will Laplace transform is IA of S. So after taking Laplace transform, this will named as equation 5 to 8. Now from equation 5 we can take a IA of S as common, and keep it in left side, other terms to the right side. So the equation 5 can be written like this. So in this equation you take RA outside, that becomes LA by RA. So IA of S is equal to EA of S minus EB over RA into 1 plus S into tau A. So this tau A we called as a electrical time constant. L by R. L by electrical time constant is L by R. Again come to equation 7. Equation 7 where we can take a N of S as common. N of S common, keeping N of S alone one side, remaining term to other side. So that becomes N of S is equal to this one. So here you can take a B outside, that becomes like this. So this J by B we can name as tau M. So this tau M we can call as mechanical time constant. This is mechanical time constant. So from equation 5 we have written IA of S. From equation 7 we have written N of S. N of S is this. So this equation 9 and 10 can be drawn. Equation 9 is related with EA and EB, that is multiplied by 1 divided by this entire thing. So that can be written. So EA minus EB, that is multiplied by 1 by R. So this entire thing, that resulting as IA of S. This is resulting as IA of S. Again back. IA of S is equal to EA minus EB multiplied by 1 divided by entire thing. EA minus EB 1 divided by entire things. So this results IA of S. Some equation 8 is IA of S is multiplied by KA pi resulting TS. IA of S multiplied by KA pi resulting T of S. Again this equation 10 is TS minus TL multiplied by 1 divided by this entire one. So T of S minus TL of S multiplied by this entire thing resulting N of S. So N of S is TL minus T minus TL over this entire thing. This is enough. Again equation 6 is N of S multiplied by Ka by resulting EB. So here we have N of S, that is multiplied by Ka by resulting EB. So this is a closed loop diagram of a separately excited DC motor. After modeling this block diagram of a separately excited DC motor, which consists of two inputs EA of S and TL. TL is the load torque and EA is the input armature voltage. By neglecting this TL load torque, neglecting this TL, this summing point is getting vanished. Now this block and this block and this block they are connected in cascade. So this can be drawn like this. Now these blocks are in cascade, which can be combined together to form like this. So this is one block. This is a feedback loop. Now by eliminating this feedback loop using the rule G divided by 1 plus GH. So this is called G. This entire thing is G. This is H. And this is G. Now by applying this G divided by 1 plus GH, this is G divided by 1 plus G into H. So here this electrical time constant tau A is very much less than mechanical time constant. So this tau A can be eliminated. So this tau A can be in this term. This tau A can be eliminated. So the term is reduces to like this. So this RAB is getting multiplied inside. Now taking this RA and this Ka by we take common outside. So 1 plus, we have the answer like this. Now this in this equation, this Ka by for this entire term we can substitute Km, and this entire thing we can substitute tau m1. So this is a transfer function of separately excited DC motor. Output is speed and input is the armature voltage. Output Laplace divided by input Laplace is equal to Km divided by 1 plus S into tau m1, where Km is this and tau m1 is this.